Okay. That's probably as good as it's going to get. Somebody was here. Here we go. I'll probably start in about a minute. Make sure everything's working properly. It actually is a little dark. Maybe, let's see. Okay, this is going to be the stream of the Chemistry Regents for August 2017. Unless asked otherwise, I'm just going to do all the questions. Let's see, answer book. Okay, to do the test, you're going to need the test, reference table, and a calculator for sure. And then you have the answer booklet also online if you choose to write the answers to the short response on that. Got nobody here. One person keeps bouncing in and out. Give it a few minutes or so. All these pens ready. And we will see. Okay, I'm going to give it one more minute. Alrighty, getting started. This is August 2017. The first question, which phrase describes an aluminum atom? So aluminum atom means we have the same number of protons and electrons. We are going to have a positively charged nucleus surrounded by negatively charged electrons. That is going to give us choice 3. That is just the definition of an atom. Just some simple vocabulary there. Then we have question 2. What is the number of electrons in an atom that has 20 protons and 17 neutrons? This right here, we are given the keyword atom, A-T-O-M. That means we are going to have the same number of protons as we have electrons, just by definition. So this guy's got 20 protons. He must also have 20 electrons. That's going to give us choice 2. Next, the mass of a proton is approximately equal to the mass of, by definition, that's just going to be a neutron, choice 2. If you did not know that, it is on table O. Table O is showing us a proton and a neutron. The number on top is the mass. Because they are both 1, we know that they have equal masses. So that is number 3. For number 4, the question asks a sample of carbon dioxide solid versus carbon dioxide gas. Because there is no bonds breaking or forming, we're just changing phase from solid to gas. We are going to have a change in particle arrangement. Solids are going to look very organized, like a checkerboard, and your gases, that's the solid, and then the gas is going to be floating all around, kind of crazy. So those particles have spread out because we have changed phases. Next is question 5. Which properties are characteristics of group 2 elements at STP? STP stands for standard temperature and pressure, which is listed on table A right here. Standard pressure is going to be 1 atmosphere, which is the pressure typically at sea level. And then we have our standard temperature, which is 0 Celsius, the freezing point of water. So group 2 elements at STP. We know that group 2 elements are in the second column on the periodic table. That is our beryllium group: beryllium, magnesium, calcium, strontium, barium, and radium. All these guys in group 2. Left side of the periodic table is going to be our metals. Metals are conductive of heat and electricity. And they have low electronegativities because they are trying to get rid of electrons, not hold on to them. So that is going to leave us with choice 1. Now, this electronegativity, if you forgot that, that is listed on table S. You can look them up element by element. Question 6, compared to an atom of carbon-12, an atom of carbon-14 has greater what? 2 things you can eliminate right off the bat are the number of protons and the atomic number, because those are the same thing. Our number of electrons is also incorrect because we are comparing atoms of each of these. And if they are atoms, that means they have an equal number of protons and electrons, which essentially makes answer choices 2, 3, and 4 all the same. I'm sorry, 1, 2, and 3 are all the same. Choice 4 is our answer, the mass number. The mass number literally is this number 12 and the number 14. It is the sum of our protons and neutrons together. Carbon has 6 protons. If you do the math and subtract, this guy has 6 protons and this guy has 8. Moving on to question 7, elements that have atoms with stable valence electron configurations in the ground state are found in which group? Okay. Stable valence electron configuration means that it has that full octet. Those are going to be our noble gases. Noble gases are found all the way on the right side of the table on group 18. So that leaves us with choice 4. Question 8, a magnesium atom that loses 2 electrons. This is MELPS. 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 Metals, electrons lose, become positive and smaller. So magnesium is a metal. It falls on the left side of the table. It is going to lose electrons. That's metal, electron, lose. It is going to become positive because electrons are negative. It's losing negatives. That means it's becoming positive. And it is also becoming smaller because it's losing that last shell. If we draw out an atom of magnesium, it is going to look something like this. Magnesium has 3 shells of electrons. 1, 2, and 3. It has 2 electrons in that outer shell. If it loses these 2 electrons, it's essentially losing the shell. So what we're left with is these 2 rings. And these 2 rings make the atom now smaller. So we have become positive and smaller. That is choice 1. Question 9. An atom of which element has the strongest attraction for electrons in a bond? This is asking you if you know the definition of electronegativity, which is a strong attraction for electrons in a bond, and then you would look all of these up, or you would know the trends. So we're looking at aluminum, carbon, chlorine, and lithium. 2 of those are metals. We know metals have low electronegativity, and we're left with carbon versus chlorine. Chlorine has an electronegativity, I believe, of 3.2. Yes, it's 3.2. And carbon is 2.6. So looking those up is one way. Also, chlorine has 7 valence electrons. It's really dying to get that 8th. She's got a high electronegativity. Next is question 10. Which type of matter cannot be broken down into a simpler substance by a chemical change? That is literally the definition of an element. That's all that question's asking. Do you know vocabulary? 11. According to table F, which substance is the most soluble in water? This is telling you exactly where to look for the answer. Very generous. So on table F, what we do is we draw a circle around our inner 2 columns. And when a substance falls in this circle, that makes it insoluble. And when things are outside the circle, they are soluble. So we are looking at silver chloride, silver, and chloride. So here are your halides, including chlorine. Chlorine, when paired with silver, makes it insoluble. That pairing falls inside the circle. It will not dissolve. It is going to sink to the bottom. Let me see if I can make this a little bit better. There we go. Okay. So those 2 pairings are going to be insoluble. Next, we have the pairing of calcium carbonate. So we are going to look at our carbonates, which are, sorry, this is all backwards. The carbonates are going to be the CO3 with a charge of -2. When that gets paired with calcium, which is a group 2 metal, not a group 1, it is going to be inside the circle, making it insoluble. Next, we have sodium carbonate, which sodium is a group 1, so sodium is going to be soluble. And just to check our work, we are going to check on that strontium sulfate. Sulfates are soluble right here. Sulfates are soluble unless they are paired up with any of these elements. Strontium, being the one in the answer choice, would put that inside the circle, making it insoluble. So according to table F, the most soluble of those listed is going to be the sodium group 1 metal paired with the carbonate. That makes question 11, choice 3. Okay, so I have been at this for 10 minutes and we did 11 questions. So that is not so bad considering it's a 3-hour test. Okay, next is question 12. Question 12, given the equation representing this reaction, which statement describes the energy change in the reaction? This is going to be BARF. So BARF stands for break, absorb, release, form. Got your message, Sarai. Thank you. BARF. When bonds are broken, energy is absorbed. And when energy, that's not how you spell. When bonds are formed, energy is released. So that's basically question 12. Here we have two hydrogens coming together. They are forming a bond. If we are forming a bond, energy must be released. So that is going to give us choice 4. Fantastic. Okay, 13. Which sample of matter is a mixture? If it is a mixture, it is not an element, and it is not a compound. So that rules out manganese, because that's an element. And then water and ammonia are compounds. You need to know the formula for ammonia. Manganese is element Mn. Water we know is H2O. Ammonia is NH3. And you know, air is a mixture of water vapor, oxygen, carbon dioxide, argon, nitrogen. Lots of different things are in air. Next is 14. Paper chromatography can separate the components of a mixture of colored dyes because the components have differences in what? Okay, so we're looking at colored dyes. How can they be separated? This is one of those things that you kind of just need to remember. Paper chromatography is used to separate things based on the molecule's polarity. Other ways we separate mixtures, we can separate by boiling point using distillation. We can separate by particle size using a filter. We can separate, how else? Filtration, distillation. We have chromatography. There's lots of different ways. But each of those separations is going to be based on one physical component of the things in the mixture. Question 15. At standard pressure, the boiling point of an unsaturated sodium nitrate solution increases when what? Okay. How do we get the boiling point of an unsaturated solution to increase? Okay. This is blurry. This is colligative properties. Colligative properties is how you can, why is this so blurry? Colligative properties is one of the ways that we can melt ice that's stuck to the road. We use the salt. Salt gets in there and expands the liquid phase. That's how I describe it. So we have, looking at just standard water. This is a regular thermometer that you can't see. Oh boy, this is going to be fun. This is a standard thermometer that, again, you can't see because I'm a knucklehead. On a standard thermometer, the boiling point of water is going to be 100 degrees Celsius, and the freezing or the melting point is going to be 0 degrees Celsius. Once we start adding salts, the liquid phase is going to expand. It is going to start boiling at higher temperatures. For example, we'll say 105 degrees Celsius, and it is going to start freezing or melting at lower temperatures. So we will say that this is maybe -5 degrees Celsius. So how this helps with ice on the road, sprinkle some salt on the ice, and now instead of it melting at 0 Celsius, it's going to, instead of freezing at 0 Celsius, it's going to freeze at -5. So if the temperature falls somewhere in this bracket between -5 and 0, your stuff starts melting. So that is that. This is upon addition of salt. And the more salt that's added, the bigger the effect. This will spread out even further. So in order to get that boiling point to go up, we are going to add more of that salt. So that is going to give us choice 4. Next, question 16. Which identifies a form of energy. Combustion is a chemical reaction. Exothermic describes energy flow, not so much energy itself. It's describing a direction that energy is moving. Thermal energy is a real thing. That is basically temperature. And then we have electrolytic, which describes a type of electrochemical cell. So that is simple vocab question. That is going to be thermal energy, choice 3. Question 17. According to the kinetic molecular theory, which statement describes one characteristic of an ideal gas system? Okay. Kinetic molecular theory is all of those silly rules that you have to remember for when you're working with a gas. So we know that an ideal gas is going to follow the rules of Plite. Pressure, low, ideal gas, high temperature. When all of this is happening, we have gas molecules that are really, really, really far away from each other, and they are moving really fast. When they are very fast moving and very far away from each other, the kinetic molecular theory is holding true. So our answer choice is the distance between the gas molecules is smaller than the diameter of one gas molecule. This would mean that your gas molecules are overlapping. That is not true. 2, the attractive force between two gas molecules is strong. Think about magnets. If two magnets are very far apart from each other, then the attraction between them is going to be very, 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 very small. These guys are far apart. They don't feel attractive forces because they're so far. So choice 2 is out. Number 3, the energy of a system decreases as gas molecules collide. Energy of a system can't really decrease unless it's going someplace else. Not great. 4, the straight line motion of the gas molecules is constant and random. That is what's true. These molecules or atoms, whatever they may be, they are like bouncy balls down the stairs. They do not do swirly motions. That is a lie. They move in straight lines. They'll bang on the wall of the container, and then they will bounce back. They'll hit this side of the container, then they'll bounce into each other, and they move in straight lines. So 17 is going to be choice 4. Okay. 18. A wonderful vocabulary question. The temperature of a substance is a measure of the... This is going to be choice 1, the average kinetic energy of the particles. Temperature measures how much they are moving. Kinetic energy is the energy of motion. Next, we have question 18. A real gas behaves most like an ideal gas when what? This is going to be Plite. When we have low pressure and high temperature, those gas molecules are moving fast and they are far apart from each other, which makes them follow the kinetic molecular theory's rules, and everything is peachy. Question 20. A reaction is most likely to occur when the colliding particles have proper energy. I just gave you the answer. They have proper orientation and proper energy. That is called the chemistry home run, or at least I call it that. When molecules, let's say we are trying to get this red atom to stick to this green atom, and this is a diatomic, let's say, and we want these two to smack into each other. If these collide like this, this first red and this first green will be able to smack into each other and have a reaction, but this red and this green will be left off into space floating around by themselves, and that is a super high energy, not going to happen type of reaction. So the best way to get these to crash into each other and have a proper reaction is if they're hitting in this way, because then this red and this green will combine, and this red and this green will combine, and then you will wind up with two molecules that look like this instead. They also, so this is the proper orientation. This way is proper. This is not proper orientation. Alongside this, they need to have proper energy. If they are not hitting with a big enough force, they're not going to be able to stick. So choice question 20 is going to be proper energy. Next, we have at STP, a 12-liter sample of methane has the same total number of molecules as. If we have 12 liters of methane, 12 liters of carbon dioxide is going to have the same number of molecules. That is Avogadro's law. When we have molecules or gases under the same conditions, these happen to be standard temperature and pressure, they're going to have the same number of molecules or particles. Next is 22. At standard pressure, during which physical change does the potential energy decrease? If potential energy is decreasing, there's two ways you can do this. First way is going to be the test taker's way. So if we are going from liquid to gas, like in choice 1, these molecules must be getting hotter. The temperature is going to rise. For choice 2, liquid to solid, they are getting colder, temperature's going down. Solid to gas is getting hotter, and solid to liquid is getting hotter. Test taker's answer would have to be liquid to solid because your temperature is dropping. It's the only one where the temperature is dropping. Other way to do this is to know that when your potential energy is decreasing, it means that your molecules are coming closer together. They're getting closer together when they're getting colder because they're not moving as quickly. Next is 23. Which equation represents a chemical equilibrium? Chemical equilibrium is your key word here. That means that we have to have a chemical reaction happening. So choice 1, we have nitrogen, liquid nitrogen, and nitrogen gas in a phase equilibrium, because the only thing that's changing between here and here is the phase of the substance. So that's out. The same is true for choice 3 and choice 4. The only thing that's changing is the phase. So that leaves us with choice 2. Stop me if there's any questions. I've just been going pretty much straight. Question 24. The amount of randomness of the atoms in a system is an indication of the. This is a vocabulary term. That is entropy, entropy of the system. Entropy is randomness or chaos. The ways to have more entropy are for the molecules to be moving faster, have a higher temperature, have more particles. It just means that they're moving around more, they're less organized. They have low entropy when they are in the solid phase, because in the solid phase, you're going to get a crystal, and that crystal is very organized. Okay, 25. 25, when a sample of calcium loses 1 mole of electrons in a reaction with a sample of oxygen, the oxygen must gain 1 mole of electrons. That is just the law of conservation. Does not matter that oxygen is diatomic. If those are the only two substances in the reaction, if calcium is losing 1 mole, oxygen must gain 1 mole. Those electrons cannot just disappear into space. 26, which reaction occurs at the anode of an electrochemical cell? This is an ox and red cat. So At the anode, oxidation happens. At the cathode, reduction happens. It's a vocab trick, sort of. So at the anode, we are experiencing oxidation. Choice 1. Number 27, which substance is an electrolyte? An electrolyte means that it will conduct electricity when it's dissolved in water, or if it is ionic, when it is molten. So we're looking for something that is either ionic and aqueous or molten. We are looking for an acid or a base. So out of all those answer choices, we are left with H2SO4, sulfuric acid. You can find that on table K. Table K gives you common acids. And we have H2SO4 right here, which is sulfuric acid. Another way to know this is an acid is because it has that H out front. According to Arrhenius, when this dissolves in water, H plus or hydronium is going to be the only positive ion that comes out or that dissolves. Okay, question 28. In which process does a heavy nucleus split into two lighter nuclei? Titration is how we determine the acidity or basicity of an unknown. Electrolysis happens in an electrolytic cell. Neutralization is acid plus base equals salt plus water. And fission is splitting nuclei. 29. Which process converts mass into energy? That is going to be the fusion of hydrogen atoms. This is following Einstein's equation, E equals mc squared, which you don't have to know how to perform, but you need to know what it's for. So this happens in the sun. We have hydrogen atoms being squished under a lot of gravity, and as they're being squished, they're moving faster, they're smacking into each other, and when those hydrogen atoms fuse into larger atoms, typically helium, there is some amount of energy that is released, and that energy is sunlight, sun heat, all of that good stuff that keeps us alive. Okay, last question of section A. Which radioisotope is used to determine the age of once living organisms? Which means that it has to be in living organisms. That is carbon-14. You cannot have life as we know it without carbon. Cobalt-60 is used in cancer treatments. Iodine-131 is used in thyroid diagnoses. That's like a gland in your throat, basically. And uranium-238 ages rocks. Okay, that is section A. We did not use anything but the reference table and knowledge of chemistry. 99% of the time, you are not touching a calculator during section A. It should be a very easy section. You should be able to get at least 27 of these questions because you only need 50 questions to pass, and this should be a very easy first 27 to get. After that, you only need 23 more for the remainder of the test. If you are afraid you're not going to pass, I very much suggest to really, really, really work on those section A questions because they're going to be the easiest ballpark questions. They're super repetitive, and if you work really hard at them, you can get your first 30. Okay. Moving on to part B1. B1 is your the rest of your multiple choice. Okay, we are looking at question 31. Which electron configuration represents the electrons in an atom of calcium in an excited state? So, calcium, according to the periodic table, is atomic number 20, which means it must have 20 electrons in its configuration. Periodic table tells us the ground state configuration, which is standard everyday calcium with no intervention. That ground state is going to be 2882. There are ways for you to memorize that. You don't have to because it's on the table. Basically, anything that gives us a sum of 20 but is not 2882 is going to be a viable answer. So we can rule out choice 2 immediately because that is the ground state configuration. We can rule out choice 1 because it only sums to 18 electrons. We can rule out choice 3 because here we just lost an electron. Actually, we lost 2 electrons. 15, 16, 17, 18. Yeah, that is still not enough electrons. And here we have our full 20. So what happened here, we had an electron from level 2 jump up to level 4, subtracting 1 from here and adding 1 there. That is calcium in an excited state. It says "an" because there's lots of different ways that calcium's electrons can move. This is just going to be a super basic one. Okay. Next, we have 32. No one has stopped me for questions at all, so I'm still moving. The table below gives the atomic mass and abundance of 2 naturally occurring isotopes of bromine. Which numerical setup can be used to calculate the atomic mass of the element bromine? Now, you could do all of these mathematical calculations and figure out which one is going to be closest to the number on the periodic table, which is 79.9. I don't recommend that because that is a time killer. Here's what you actually do. You do the mass times the abundance and then add it to this mass times this abundance. So that is going to be, also you have to change this percent into a decimal or you have to divide by 100. Either way works. So here we are doing the 78.92 times 50.96, which is mostly correct. They just didn't divide by 100 here. So I'm going to rule out, I'm going to rule out that choice because they did not convert that percent back into a decimal. That is no good. Then here we have 78.92 times 49.31. Those two data sets do not match. They swapped the data for choice 2. Choice 3, we have 78.92 times 0.50.69. So in moving the decimal 2 to the left, we have divided by 100. So that's good so far. And then we have that 80.92 times the 49.31% written as decimal. So that is choice 3. That's where everything pairs up just as it should. Okay. Next, we have question 33. These diagrams represent substances that have what? Okay. These are called allotropes. allotropes. This is used all the time. They use either O2 and O3, which is oxygen and ozone, or they are going to use diamond and graphite. Graphite like in a pencil. So what happens? They technically are the same element. They are forms of the same element. They are not they're not different compounds, but they're the same element. And this is why it's weird. So we see oxygen here. We have one double bond, and each of these oxygens has 2 electrons. This is the oxygen that we breathe. These are diamond and graphite. So diamond, when we have like a crystal structure for diamond, it almost kind of looks like these carbons form diamonds, and then they interlock. And that's why diamonds are so strong. And this is what they do over and over and over, and they work in different dimensions as well. So they'll have in front and behind, and they all interlock. Diamonds are crazy strong because of the way this works. Graphite kind of looks like a honeycomb, like it makes hexagons, and they all kind of like lay on top of each other, and then they lay in sheets, which is why a pencil will glide and smudge on the paper. What's actually happening is that the little graphite molecules are sliding off of each other. If you ever open up a pencil sharpener and unplug it before you start sticking your fingers in it, but in the blades, when you get this graphite, it's almost like greasy because these layers just slide off of each other. So those are called allotropes. Basically what it is, it's still an element, but the structures are built differently. And because they're built differently, they have different properties. They gave you a picture of it here. Obviously, you can see that they have different molecular structure. And because they have different structure, they are going to have different properties. That's going to be choice 4. Okay, moving on to 34. Okay, I have a few people adding in for reference. This is August 2017. All right, 34. What is the chemical formula for titanium 2 oxide? This 2 right here in Roman numerals is telling you the charge on the titanium. So you would uncrisscross this or reverse drop and swap. Or you can look at the periodic table, which is always the better thing to do. Titanium plus 2, it has to be plus because it comes in front and it's a metal. And then we have oxygen. If we look up oxygen on the periodic table, its charge is only ever going to be -2. That's what this itty bitty tiny -2 is for. Then we crisscross these. Why is it so blurry? We are going to crisscross these, just the number, not the charge. Crisscross those, we are going to get Ti2O2. Now, because this is ionic, meaning it's a metal bonded to a non-metal, these come in a crystal lattice, which looks like a checkerboard. So we would have a titanium atom next to an oxygen, next to a titanium, next to an oxygen, and so on and so on. So because these are checkerboards and it's ionic, instead of looking at this 4 block, we reduce it into just the 2 block. So we reduce these. 2 goes into 2 one time, and we are going to get TiO as the final formula. Why is this so blurry? It's driving me crazy. There we go. So TiO is going to be choice 1. Question 34, choice 1. All right. Moving on. Question 35. Which equation shows a conservation of mass and energy for a reaction at 101.3 kilopascals and 298 Kelvin? Boy. Okay. Conservation of mass is easy. We are just making sure that the equation is balanced. So we need the same number of hydrogens on both sides and the same number of oxygens on both sides. So here we have 4 hydrogens, 2 oxygens. 2 times 2 gives me 4 hydrogens, and 2 times this imaginary 1 down here is going to give me 2 oxygens. That one is balanced in terms of mass. Here we have 4 and 2, 4 and 2, 2 and 2, 2 and 1. 3 is out because we don't have the same number of oxygens on both sides. And here, again, we have 2 hydrogens and 2 oxygens, giving us 2 hydrogens and only 1 oxygen. So this guy is also out. Then the next question is, how do we decipher between choices 1 and 2? This would take me to table I, because I've seen a bunch of equations that look kind of like this on table I, and I would start looking at those numbers. So let's compare. Table I has all of these wonderful heats of reaction, and we are looking at hydrogen and oxygen. So let's start there. Hydrogen and oxygen. Here we are looking at hydrogen gas, and oxygen gas is the first one. Hydrogen gas, oxygen gas becoming water vapor. And this is showing us that it is, I'm sorry, you're not even looking at it. This is showing us that this equation is going to give us a negative 483.6 kilojoules of heat. Now, if this is negative, that means that it is an exothermic reaction. The heat is coming out of the equation. It's exiting. It reminds you of this on the bottom. A minus sign indicates an exothermic reaction. Exo, heat is exiting. So if heat is exiting from a reaction, it is going to be a product. It's coming out of the reaction. So I'm inclined to pick choice 1, but I'm just going to check on choice 2 to make sure. So we have hydrogen gas and oxygen gas becoming liquid water. We're going to check that out. Hydrogen gas and oxygen gas becoming liquid water. That is giving us negative 571.6 kilojoules. This is not quite the same number. This is actually half. What is 571 divided by 2? Yeah, that's going to be this number. So what actually happens, this heat value would work if this was 1 mole of hydrogen gas and half a mole of oxygen gas. And then we would get the 1 mole of H2O, that's liquid, and then the 285.8 would come out. Half the heat is going to give me half the product. So according to table I, my answer choice is 1. Moving on to question 36, always one of my favorite questions. Which 2 particle diagrams represent a sample of one substance? A substance is going to be not a mixture, basically anything but a mixture. So we are looking at either a compound or an element. Now, choice 1 is giving me diatomic chlorine. That's what these stripes are. Why is this so blurry? There we go. Okay, so that's giving me diatomic chlorine and a molecule of H2O. So this is chlorine and water, and that is a mixture of chlorine and water. So that is a mixture, and it is a mixture. It is not a substance. Roman numeral 3 is diatomic oxygen and diatomic hydrogen. Yes, this live stream is going to save. They don't always save. I had to ask it to save, but I did. I made sure that it saved. And there's also 3, maybe 4 old ones. I think I have an August, a June, and a January, but I figured August is tomorrow. We'll do an August now. You are very welcome for the stream. Okay, so this is a mixture. This mixture makes it not a substance. Then we have only H2O. This is a compound, and if this is a compound, then yes, it is a substance. Substances are pure. And then here we have a bunch of diatomic chlorines, Cl2. That is a diatomic element. And if it is a diatomic element, or any element for that matter, it is going to be a substance. And what goes with this? Roman numeral 2 and Roman numeral 4. That is choice 4. Diatomic elements. There are 7 of them. Where's the periodic table? There's two ways to know your diatomic elements. Diatomic elements are, they form a 7, starting with number 7, and there's 7 of them. These are 6 of your diatomics, forming a 7, and then you add in everybody's favorite gas, hydrogen. So those are your diatomics, hydrogen, plus a 7 starting at number 7. Or you can remember Brinkelhoff. BRINCLHOF. And then obviously these all have the 2s because they are more happy when they are bonded to themselves. The halogens, fluorine, chlorine, iodine, and bromine, these guys form diatomics because they have 7 valence electrons and they're looking to get that 8th, so they bond with each other to share that 8th electron. Nitrogen has 5 electrons. It will triple bond with itself so that it's the 5. It has 5 and then it bonds 3 times so that it gets its 8, and then it has 2 lone pairs. 1 lone pair, I'm sorry. I'm going to draw it right here. Actually, this pencil might be too, oh no, it's not. Okay, so the way that you look at nitrogen is that, okay, the way you look at nitrogen is that for each of these lines, this nitrogen, this half, and this half of the nitrogen belongs to this guy, and then these are his original. So he put in 1, 2, 3, 4, 5. And then this nitrogen over here put in 1, 2, 3, 4, and 5. So this combination gives everybody 8. There's 2 electrons in each bond, a blue one and a pink one. That gives everybody 8. And then for the oxygen, his is kind of opposite. He puts in 1, 2, 3, 4, 5, and 6. And this oxygen also puts in 6. Why is this so blurry? 1, 2, 3, 4, 5, and 6. And then these electrons that they share get swallowed up in a bond. That's the easiest way to draw Lewis structures, just FYI. So these are covalent Lewis structures. These oxygens in total get their magic number 8. They put in 6 and they share 2. And then your halogens are all pretty simple. Same with the hydrogen. Those Lewis structures, they all look the same. Fluorine bonds with fluorine. 1, 2, 3, 4, 5, 6. So this fluorine, the blue fluorine, let's say, put in this electron here, and the pink fluorine put in this electron here, and then those 2 electrons got swallowed up by the bond. That's how you draw a Lewis structure. Okay, moving on. We are up to question 37. Ooh, I like this. According to table G, which substance forms an unsaturated solution when 80 grams of the substance are stirred into 100 grams of water at 10 degrees Celsius? Lots of numbers here. We are looking at table G. Table G is a mess. I hate it. I would have preferred like 10 mini graphs as opposed to all these stupid lines all crisscrossing. Hopefully you can see. Okay, table G works on 100 grams of water or 100 milliliters of water. Occasionally, they'll have you double this to 200 grams of water or half it to 50 grams of water, in which case, whatever data points you get, you cut them in half or you double them, depending on what you do. In this instance, we are looking at which substance? Oh, this is a pain in the neck. Okay, so we're looking at 4 different substances. We're looking for an unsaturated solution when we have 80 grams at 10 degrees Celsius. So we're looking at this point right here that I've put a big dot on. And we're asking which of these 4 solutions is going to be unsaturated at this point, which means that this point is underneath the line. On the line means it's saturated, can't hold any more stuff. Under the line is unsaturated. And then sometimes you get super saturated, but that's kind of a iffy thing. So this point for KNO3 is this big curvy line here. This point is over the line for KNO3. KNO3 is like crazy, like really saturated at this point. So that answer choice is out. Potassium iodide, Ki, is all the way up here. This thing is crazy soluble. If I put in 80 grams of Ki in water, then I could still add more salt, until this much salt actually, until the Ki is saturated. Now, over the line is not necessarily super saturated. Here's how it works. Saturated means it can't hold anymore. So if I have a solution of, oh boy, if I have a solution and we have some water in here and I've dissolved some stuff and stuff went in and I stir it all up and nothing is sitting on the bottom, this is unsaturated. If I have a solution and I have water in here and I have some stuff and I go to dissolve it and then I stir it up and it's still sitting on the bottom, think of like a glass of chocolate milk when you get to the bottom and all that syrup is sitting on the bottom. This is saturated. This is any point over the line. And this is below the line. Supersaturated is entirely different. If you notice, this first solution is going to be homogeneous. That is because it looks the same throughout. This saturated is going to be heterogeneous because you have a solid layer on the bottom and an aqueous layer on top. Then supersaturated looks like this. You have stuff, you want to dissolve it, it goes in. But this solution is crazy hot. If this solution is super, super, super hot, and I add all this stuff, the water molecules separate, and all of this salt can fit in between where it otherwise wouldn't be able to. So because this is super hot, all of this salt, even though it maybe shouldn't have dissolved, is going to be able to dissolve. So this is a point over the line, but they have to tell you in some way that it is now homogeneous. Sort of like saying the solution was tricked into holding more salt than it should be able to. That's how I like to describe it. This is how they make rock candy. They dissolve a lot of sugar in the water, and then they put kind of like a popsicle stick in there, and the sugar, as it starts to undissolve, gets stuck to the popsicle stick and makes rock candy. That's how they do it. So this solution was kind of tricked into holding more salt than it should. So they have to tell you that the point is over the line, and in some way they have to tell you that it's homogeneous. There's nothing sitting on the bottom. Okay, Just want to clear that up because a lot of people say over the line is 100% saturated, and that's not always true. Sometimes it's super saturated. So going back to question 37, that was answer choice 2. Answer choice 2, Ki is way up here, and the point we were talking about is way down here. So we could add more Ki before stuff starts to sit on the bottom, which would make it unsaturated. That is choice 2. Okay. 38. What is the concentration of sodium chloride in an aqueous solution that contains 1.2 times 10 to the third gram of AgCl, I'm sorry, to the negative third gram of AgCl in 800 grams of the solution? Blech. Okay. The units here they give us are parts per million. Anytime I have to do math, I flip to the back cover, which is table T, gives me all the equations I need. So on table T, oh, also, if you forgot what ppm is, you have all of your units on table D. Selected units, they tell you pretty much everything you need to know. ppm is right here. That's parts per million, and it's concentration. So got my units, flip to the back. Concentration, parts per million. This is the equation I want to use. So I'm just going to plug in those numbers and find out what the concentration is. We were given the numbers. 1.2 times 10 to the minus third of AgCl over the grams of the solution. They said we had an 800 gram solution. Sometimes you have to add these things, sometimes you don't. This says specifically that this 800 grams is the solution, which means that's just the number that goes on the bottom. I'm going to do this, and according to the equation, I'm going to take all of that and multiply it by 1,000,000. If you don't know how many zeros are in 1,000,000, I feel sorry for you because somebody is going to write you a check for $1 million and only put 3 zeros on it. Make sure you know it's 6 zeros. So I'm using a crappy little calculator. I'm going to find my scientific calculator. Here we go. Okay, so we turn the calculator on. We are doing, in parentheses, 1.2 second E minus 3. That E means times 10 to the, and then you just plug in your exponent. How do you get the E? Second, and then the x to the minus 1. It says the little EE over the top. And this is a TI-30X 2S. I don't know. If you're not comfortable using E, you can use times 10 caret raised to the minus 3. You could do that as well. No issues. Take that number, close the parentheses, and divide by 800. You're going to get 0.00000015. You could also do this in scientific notation. Second, science or English, switch to science, and that's what you're getting. 1.5 times 10 to the minus 6th. You can do that as well. I'm going to stick with the standard. Now I'm going to take this number and multiply it by 1,000,000. 1, 2, 3, 1, 2, 3. Very simple. Hit enter. We are getting 1.5 parts per million, which is choice 2. That's just a calculator question. They just want to know that you can plug these numbers into an equation and work a calculator. There's almost no chemistry knowledge to that. It's just reading the tables and punching the numbers. Okay. Moving on to question 39. A sample of gas in a rigid container with a movable piston. The pressure of the gas is kept constant. If the Kelvin temperature of the gas is doubled, what is the volume of the gas going to do? Okay. This is a math question. We are going to work on the combined gas law. Combined gas law is on table T. It's right here. PV over T1 equals PV over T2. Tells you what they're all for. So PV over T1 equals PV over T2. That works for me. Then we are saying we have a sample of gas in a rigid cylinder with a movable piston. That means it's like a thermos, like a coffee cup made of metal, but there is a plunger in it that can go up and down. So it kind of looks like a syringe where you can squeeze. This is where the gas is. If you push down on this, you can squeeze the gas. And if you pull the piston out, you expand or you give the gas space to expand. So our volume, the amount of space it takes up, can change. Then we have the pressure of the gas is kept constant. If the number is the same on both sides, we can cancel it out. This is saying the Kelvin temperature of the gas is doubled. So let's do this. I have, just for fun, I'm going to say my Kelvin temperature started at 100 Kelvin. And then I'm going to double it. In order to get the numbers to be the same, to get this fraction to equal this fraction, what would my volume have to do? That's what the question's really asking you. So plug in a number for volume 1. Say it's also 100, because 100 is an easy number to work with. If this volume is 100, 100 divided by 100 gives me 1. What would V2 have to be so that that number divided by 200 would also give me 1? This number would have to be 200, which means that the volume of my gas would have to double. So that is choice 2. That is a math brain thought experiment type of thing. It's equivalent fractions. It's something that you've been doing since like 4th grade. They just put it in chemistry terms. Okay, question 40. What is the amount of heat required to completely melt a 200-gram sample of water or ice at STP? Okay, this sounds similar. The amount of heat required. Heat required is going to send me back to table T. There's a section here called heat. I am looking to melt a sample of ice. If I am melting ice, I'm going to use the heat of fusion equation. Melting and freezing are opposites. Freezing and fusion, they both start with F. That's the best I can kind of give you on memorization for that. We are going to melt. Let's see, we are using the equation Q equals MHF. Q is the heat, M is mass, HF is the heat of fusion. All that's listed for you on table T. What is the amount of heat? They want to know Q. M is 200 grams. And HF is a constant. I can find that on the front cover. Heat of fusion of water is 334 joules per gram. Plug this all in. Q equals 200 times 334. Plug in your units or not, doesn't matter. They only want the answer, doesn't matter about the process. 200 times that 334 is going to give me 66,800. And that value is joules. Sometimes you need to convert this to kilojoules. That's King Henry drinks unusually delicious chocolate milk. Joule is a unit. So I'm going to jump 1, 2, 3 spaces to the left. My decimal's back here. I'm going to move it 1, 2, 3 spaces to the left. This would be equal to 66.8 kilojoules. Not relevant for this question, but maybe on others. Answer choice here is going to be number 3, which is that 66,800 joules. Still nobody's asking questions, so I'm moving on to 41. as a 15.1 gram sample of metal absorbs 48.75 joules of heat. Its temperature increases by 25 Kelvin. What is the specific heat capacity of the metal? Okay, again, talking about heat. I'm going to go back to table T, where we're talking about heat here. Specific heat capacity is variable C, which means I'm going to use the equation that has variable C. Q equals MC delta T. Some of you may know it as MCAT. That's fine. No difference. The math comes out the same. So I'm going to do Q equals, sorry, I'm just trying to straighten this out. Q equals MC delta T. The question says the mass was equal to 15.1 grams. It absorbs heat, 48.75 joules to be exact. And the temperature increases. The change in temperature is a positive 25. It is increasing by 25, and that is in Kelvin. What is the specific heat capacity of the metal? They want to know what is the value of C. So I'm just going to plug in everything I know. Q, 48.75 joules. This is equal to 15.1 grams. C is what they want to know, and the delta T they told me is 25 Kelvin. I'm going to do 15.1 times that 25. 48.75 is equal to 377.5 C. I combined those two values. This is a separate thing. I combined those two values by multiplication. Got this here. Then to get the C by itself, I'm going to divide on both sides. 48.75 divided by 377.5. C is equal to 0.129. Significant figures. I should have 3 because my mass was given to 3 sig figs, which is the lowest value here. This is considered, well, this is actually 25.0. So these two tie. This is what I'm getting. The units on this are going to be joules per gram times Kelvin. And that is answer choice 1. Okay, 42. Given the formula, what is the chemical name of this compound? Okay, I have 3 carbons. Prefix for 3 carbons is prop. That comes from table P. When I have 3 carbons specifically, I'm using the prefix prop. I have a double bonded O on the end of this molecule. Looking at table R, I'm looking for the double bonded O on the end of the molecule. This H here is telling you this is the end. It's different from a ketone because the ketone has these open ends, which means that the double bonded O goes somewhere in the middle. This is going to be an aldehyde. The ending on an aldehyde is anyl. So this is going to be propanal, which is choice 2. This is literally the example that they give you in the reference table. Sometimes you hit the lottery and you get questions that are just reading. Okay. Next is 43. Given the equation representing this reaction, what type of reaction is represented by this equation? Okay. Whoa. Basically what's happening is that we have this chlorine and this hydrogen swapping places. That's sort of what happened. This hydrogen and this chlorine swapped places. Think of it like sports. If 2 players are going to swap places. One's on the bench, one's on the field, and they switch them. They call that a substitution. You're subbing in one for the other. When your teacher is absent, they take out one teacher, they put in another one. That's a substitute. Easy as that. 44, atoms of which element react spontaneously with magnesium? Okay, this is table J. On table J, which is kind of a pain in the neck because there is no numbers on it, and it's sort of just like, hey, look at all these letters. Kind of sucks. Okay, which element reacts spontaneously with magnesium? Magnesium is right here. We are comparing chromium, barium, iron, and zinc. Okay, test taker. Which one of these is not like the others? Okay. You have 3 elements that are below magnesium. You have 1 element that is above magnesium. What happens? The barium is more active. It is wanting to react with stuff. It is going to react with the magnesium. It kind of like picks on the magnesium and is like, hey, give me your electrons. Magnesium does the same to things that are lower than it. If you notice, copper, silver, and gold are on the very bottom. These are called the coinage metals because they're super, super stable. They don't want to react with anything. The gold that is in the pyramids of Egypt is just as beautiful and shiny as it was when they put it in there over 2,000 years ago. The iron that they use to make bridges is crappy and corroded. Lithium is in batteries because it's super reactive and it's trying to move electrons and create an electric current. The things that are on top are more reactive. Barium wants to react with magnesium. Magnesium doesn't necessarily want to react with barium, but barium's a big bully and forces magnesium to react. So that is going to be choice 2. And a lot of these questions you'll find are just, I would say it's like 3 or 4 per test are just test taker type questions that you didn't need to know any chemistry for that. For this question, you just needed to know to look at table J and then figure out 1's on top and 3 are on the bottom. It's just kind of the way that it works. Question 45, we have a titration, 5 mils of a 2 molar sodium hydroxide solution. It's exactly neutralizing 10 mils of a hydrochloric acid solution. What's the concentration? Okay, you are given the term titration, and you're given a bunch of numbers. So you should check the titration equation, which is on table T. Titration's back here. We have molarity and the volume of an acid is going to be equal to the molarity and the volume of a base when they are exactly neutralized. So MVA equals MVB. And there's a few ways you can set this up, whatever floats your boat. I like to do the acid and the base, and we have a molarity of the acid. The molarity of the acid is what we're solving for. The volume of the acid they gave us was 10 milliliters. The molarity of the base was 2.0 molar, and we knew that we had 5 milliliters of it. Some of you already know what the answer is. You don't need to do the math. Molarity of the acid times the volume of the acid is going to be equal to the molarity of the base times the volume of the base. That's not what I wanted to do. I wanted to do 5. 2 times 5 is giving me 10. This is 10 M. M in that case is equal to 1 milliliter. Not milliliter. Molar. This is a 1 molar solution of sodium hydroxide. That is choice 1. Simple multiplication. Okay. The hardest part of this is just knowing where to look for your equations and your answers. The easy part is doing the math. This is math that you've been doing since 6th, 7th grade. They just made it chemistry. You just need to know which one's the acid, which one's the base, and where the equation is. That's the hard part. Okay, we're moving on to 46. Given this equation representing a reaction at equilibrium, also indicated by this double-sided arrow, if an acid is defined as an H plus donor, what is the acid in the forward reaction? Forward reaction means you're reading it from left to right. Question is, which of these is giving up an H plus? Which of them is the acid? So in order to do this, you do a before and after. I'm going to rewrite this nice and big. NH3 and H2O is in equilibrium with NH4 and OH minus. Okay. Here's our big equation. This is how you do these. These are the Bronsted-Lowry acids and bases. Remember, bad bases accept, acids donate. They're going to donate a proton, which is also called H plus. Your bases are going to accept that H plus. So I always look at chemical reactions as a before and after. We have NH3 becoming NH4. In order for that change to happen, it had to have had accepted the H plus. It literally gained an H. So if NH3 is gaining, that makes NH3 the base. Then if we have things that look alike, H2O kind of looks like OH minus. Between these two, to get from here to here, it had to have lost that H plus, which means it donated it. So if H2O is donating the H plus, that makes this your acid. So in this case, water is acting as your acid. 46 is going to be choice 2. Water is donating that H plus. Okay. Question 47. Compared to a solution with a pH value of 7, a solution with 1,000 times greater hydronium ion concentration would have a pH value of what? If you remember the pH scale, I'm going to draw it real tiny down here. pH scale runs from 0 to 14. Low side is your acid, high side is your base. 7 in the middle is neutral. Now, this is a pH scale. P in chemistry means negative log. So on a log scale, the difference between 7 and 8 is going to be a factor of 10 because it's a negative log scale. As your hydronium goes down, as H plus goes down, your pH value goes up. It's kind of backwards. That's where the negative comes from. And in a log, the difference between the numbers is 10, where all of your linear scales, like from first grade, when you were adding 2 plus 2 and you would count on the number line and you do the jumps, those are linear. The difference between every number is 1. On a log scale, the difference between every number is 10. And instead of adding, you either multiply or divide. So our hydronium, we're adding more hydronium. That means our thing is getting more acidic. We want to move down the scale. For it to be 1,000 times greater, we are going to jump from 7 to 6. That's 10 times. From 6 to 5 would be 100. 10 times 10. And I don't know why you would want to do this on the calculator. You could, but they don't put the formula on the reference table, so you would have to know the formula. To move from 5 to 4 would be 10 times 10 times 10, which is giving you that 1,000. So your pH value would be 4. Let me circle it in a different color. If you really wanted to do this in the calculator, you totally could. That equation would be pH equals negative log of the H plus ion concentration. Okay. Question 48. Which Lewis dot diagram represents the bonding in potassium iodide? Okay, potassium iodide. Potassium is K plus 1. Iodine is going to be minus 1. They crisscross, and they are going to get a singular Ki. Because K is the metal, it gives away its electrons, and I is going to gain those electrons. So what happens, I'm going to kind of draw it out here. Potassium has 1 valence electron. Iodine has 7. Potassium is trying to get rid of this electron, gives it to the iodine. Iodine accepts it. K is then left with a plus 1. Iodine has those 8 electrons. You do not have to differentiate between them. You don't have to do the dots and the X's. Those are your 8 electrons, and then you use the brackets to hold all of your electrons together, and that's a minus 1 charge. This diagram corresponds with choice 1. That's the wrong marker. Boom. That simple. Okay. 49. Table below shows properties of the compounds at standard pressure. We don't know what the 2 compounds are. Okay, so here for compound 1, we have a decently high melting point and a decently high boiling point. We know it is a good conductor of electricity when it is a liquid or when it is aqueous. This should shout to you ionic. And the next thing we have is a super low melting point, like -Celsius, and a not too high boiling point, which means it's probably going to be a liquid at room temperature and very easy to boil. My guess would be like acetone, like nail polish remover. Like it's liquid for the most part, but it'll evaporate really easy, low vapor pressure, kind of stinky, that type of thing. So that is going to be organic, covalent. Covalent describes bonding. It does not describe a compound. So covalent, when we use it to describe compounds, would be a molecular compound, and ionic describes both the bonding and the compound. So we are going to say compound 1 is ionic and compound 2 is covalent or molecular. Choice 3. Moving on to question 50, last one of the multiple choice. Given 2 balanced equations, each representing a reaction, which statement compares the energy in terms of these 2 reactions? So we are looking at 1, a radioactive reaction. We have radium transmutating or turning into radon as it emits alpha particles. And this is nuclear. It's a nuclear reaction. And for this one, we have a hydrocarbon fuel burning in the presence of oxygen. This is going to be a combustion. So both of them are high energy, but that nuclear reaction is going to be like much higher. So we have equation 1 has more energy. No, these are not having energy absorbed. These are having energy be released because the energy is products in the reaction. That means that energy is coming out. So if the energy is coming out, that energy has to be released. Choices 1 and 2 are out. Equation 1 has more energy being released, which is true. So that is choice 3. Equation 1 has more energy being released. Okay. That is all of part B1. We're going to take like a 2-minute break and start with the short response. So If you don't already have one printed, I would suggest that you print the answer book because it helps guide how you write the answers. Here you have two different things. It tells you the units for the questions. Specifically, question 69 has you balance an equation. And 83 has you finish an equation. They don't give you this in the regular test. So I would print this, or at least have it open. This is going to be your answer booklet if you're looking for the document. Again, it's August 2017, and I'll see you in 2 minutes. Alrighty, let's get back to it. Get this over with. Okay. Question 51 and 52 go together. Okay, so we got this molecule. We know it's organic. It's a carbon chain. We got this double bonded oxygen and the nitrogen. State the type of chemical bond between the hydrogen and the nitrogen. So, can we take a break like this for the test? Technically, in the Regents exam, there are no like scheduled tests, rests rather, but you're welcome to get up and use the bathroom, take a short walk out in the hallway, go stretch. No one at our school is really going to stop you from doing that, provided you're not being a knucklehead in the hallway. But no, there are no scheduled breaks. So anyways, the type of bonding between the hydrogen and the nitrogen, there are a few answers. You could write covalent. You could write single bond. Just write one answer. Don't write multiple. That's all I would write. Those are the only two things that I would possibly write. So that's number 51. For 52, explain in terms of charge distribution why a molecule of butanamide is polar. Okay, we're talking about a molecule being polar. This is going to be SNAP. When things are symmetrical, they are nonpolar. And when they are asymmetrical, they are polar. So this is telling you the molecule is polar. It's asking you why. And the reason is because it is asymmetrical. No one says that these answers have to be in full sentences. You can write as little or as much as you like. I suggest write as little as possible. One, because you don't have to. Two, because sometimes you wind up talking yourself into a wrong answer. You over-explain, and it turns out you explained it incorrectly. And no one told you you had to. Rest your hands. You don't have to write that much. Okay, so in terms of charge distribution, why is this molecule polar? Asymmetrical. I would accept just asymmetrical. Just to be safe, I would say asymmetrical charge distribution. Done. Does not have to be in complete sentences. You don't lose points for writing a fragment. So write a fragment. It's fine. Okay. Question 53. We are looking at a system in equilibrium in a sealed rigid container. Sealed rigid container means constant volume. And it's represented by the equation below. Compare the rate of the forward to the rate of the reverse. I have asked this question in my classroom 175 times. Every single one of my students should be very quick to this. There are two things with equilibrium. Your concentrations are constant. Your carbon monoxide is always going to be constant. No matter what that concentration is, it's going to be constant. And your rates are going to be equal. These reactants come together at the same rate that these products are breaking apart. So your concentrations are constant, but your rates are equal. And that's all you need to write for your answer. Equal. Question 54, state the effect of the concentration of H2O and CO2 when more H2 is added to the system. So if I am adding more H2O, oh, I did that backwards. I'm sorry. Let me redo this. We have carbon monoxide and H2O, CO2, and H2. This is saying I'm adding more H2. So as the H2 goes up, what is happening to H2O and CO2? Okay. If I'm adding more H2, that H2 is going to react with the CO2. And if the CO2 is being used in a reaction, its concentration is going to go down. Again, that H2O the H2 hydrogen has been added. I have extra hydrogen lying around. It is going to start reacting with the carbon dioxide and use it up. So the carbon dioxide is going to decrease. I'm going to write that right now. Carbon dioxide decreases. You can put goes down. You can write gets used up. Anything to that effect. Then, if my H2 and CO2 are having reactions, they are becoming something new, that would mean that I am going to have an increase in my hydrogen, in my water, rather. Water is going to be formed by using up the carbon dioxide and the hydrogen. So water is going to go up. It is going to increase, go up, be formed, anything to that effect. Increase and decrease is probably your best answers because your graders won't have to think about whether what you're saying is correct or incorrect. But if you're having a brain blub and you can't think, other terms will work. Okay. Next, we are up to 55. 55 through 58 get grouped together. So, We have a table containing selected information about chlorine and 2 compounds containing chlorine. One piece of information is missing for each of the substances in the table. Identify the phase of chlorine at STP. Okay. My students should just know this off the top of their heads. Chlorine is a gas at room temperature. It's mustard gas from like World War I. All the same thing. Terrible yellow colored gas, super poison. For 10 seconds, I'm going to go over the phases of the periodic table. Gases, hydrogen, helium, nitrogen, oxygen, fluorine, chlorine, and then all of the noble gases, obviously. I honestly don't know about 118. It's probably a gas. But those are your gases. Then your liquids are going to be bromine, which is like a yellowy, not yellow, kind of like a reddish brown liquid. And then we have mercury, which is Hg. That's your liquid metal. And then gallium is kind of weird. It has a super low melting point. So it's liquidy, but it's not necessarily a liquid. And then the rest of the table is all metals. Not all metals. They're all solid. So iodine is going to be a solid. Gallium technically is a solid, even though it has a super, super low melting point. And then the rest of the table, I could color it all in, but those are all going to be solid. But the important ones really to know are your gases, which are hydrogen, helium, all of the noble gases, and then these 4 right here, nitrogen, oxygen, fluorine, and chlorine. You could also look this up on table S. For table S, chlorine has a boiling point of 239 Kelvin. Standard temperature is 273. So what was that, 239? 239 is below 273, which means it's a gas at room temperature. For those of you who just don't know. So 55 chlorine is a gas. And that's all you have to write, just gas. No sentences, that's fine. 56, determine the molar mass for calcium chloride. Calcium chloride, it gives you the formula right here. Calcium chloride is CaCl2. Molar mass means add up all the pieces from the periodic table. So there's a lot of paper for this test. Calcium, I'm just going to do it on the side here. Calcium and chlorine are my 2 different elements. I have 1 calcium atom. Its mass is 40. You can operate in whole numbers. That's fine. 1 times 40 equals 40. For chlorine, I have 2 chlorine atoms. Its mass is 35.4. You can round that to just 35. You can round it to 35.5, whatever you like. 2 atoms, each with 35, is going to give me 70 in total. 40 and 70 is going to give 7, 8, 9, 10, 11 is going to give me 110 grams per mole. On the answer book, it tells you the units. You don't have to know them. One of the great things about chemistry, the answer is 110. Just add up all the pieces. Next is question 57. It says the liquid compound, which is 1,2-dichloroethane, has an empirical formula of CHCl. Write the molecular formula for this compound. This is a toughie. So the empirical formula is the most basic formula there is. I call it the skeleton formula. We are looking at a carbon, hydrogen, and chlorine. They are all working in a 1:1:1 ratio. which is indicated because there's no numbers down here. We need the molecular formula for this compound. Our molar mass is 97. Okay, you technically don't have to do math for this question because it told you what the formula is. Why would they do that? That's kind of silly. Okay, so here we're going to add up a carbon, which is 12, a hydrogen, which is 1, and a chlorine, which is that 35. Add this all up. I can't do math in my head because probably I was dropped as a child. Who knows? This adds up to 48. And I know that the molar mass is actually 97. So I'm going to do 97 divided by the 48. This is the empirical and the molecular. 97 divided by the 48 is going to give me basically 2. It's 2.02. It's essentially 2. So what I'm going to do is take this 2. I'm going to multiply it by the formula, which means my actual formula is C2H2Cl2. Now, that's what I got from doing the math. This question, whoever wrote this, probably got yelled at because it's not a very, it is a good question. It's not a bad question by any means, but there's multiple ways to solve it, which means it's testing you in different areas at the same time. The other way to do this without doing math for this particular question, it told you the formula was 1,2-dichloroethane. Ethane means you have 2 carbons. I'm going to draw them. They're bonded together. It also told me dichloro. I have 2 chlorines, 1 on carbon 1, 1 on carbon 2. CO and CO. Oh, this is not ethane. This is ethene. That's why it's wrong. Okay, so this is ethene. Ene means that these carbons are double bonded. So each carbon is supposed to have 4 bonds. So far, each carbon has 3. I'm going to add 1 hydrogen to each so that all of my carbons have 4 bonds. 1, 2, 3, 4, and 1, 2, 3, 4. This is the same formula I got from doing all that math, which is C2H2Cl2. Yeah, whoever wrote this question is kind of a dum-dum. I mean, it's not a bad question. It's just they're asking you. You can solve it in 2 different ways. So it could be an empirical molecular formula question where you have to use like math and stoichiometry, or it could be an organic chemistry question where you decipher what the molecular formula is based on its name. So there's 2 ways to do that one. The answer is the formula. That's what they want to know. You're not drawing it, you're writing it out. So this one would be C2H2Cl2. And the last question is 58. Explain in terms of electrons why the compound containing calcium and chlorine is classified as an ionic compound. Calcium and chlorine is ionic. Why? In terms of electrons. So we know that ionic 99% of the time is a metal bonded to a nonmetal, which is true, but that doesn't answer this question. It says in terms of electrons, which means that your answer must talk about electrons. If you don't use the word electrons, you're not answering the question. So what actually makes something ionic is that electrons have been transferred. Electrons are transferred. You do not have to write this in a full sentence. This compound is ionic because blah, blah, blah. No one cares. Electrons are transferred is all you need to write. Keep it simple. All right. 59 and 60 are the next question set. Here we are being asked, we have an equation below representing the reaction between 2-methylpropene and hydrogen chloride gas. Explain in terms of chemical bonds why the hydrocarbon is unsaturated. Okay. First thing, this is asking about a hydrocarbon, which means the compound has only hydrogen and carbon. This one contains chlorine. This one contains chlorine. It's not talking about this, and it's not talking about this. It's only talking about this one. Why is this molecule unsaturated in terms of chemical bonds? Which means, say the word bonds in your answer. Anytime it says in terms of, it basically says use the next word. So, why is this unsaturated in terms of bonds? There's a few ways to write this. And I'm going to write them all. First answer. There is a carbon-carbon double bond. You have to explain. So you can't just do C double bond C. That's not an explanation. You have to explain it. There's a carbon-carbon double bond. You can say there is a carbon that can bond to more hydrogens. That is this carbon and this carbon. Actually, you would say there are two carbons. That's pretty much it. I would go with the first one, carbon-carbon double bond. Probably the easiest, most straightforward. Identify the class of organic compounds to which the product belongs. This is the product, the green one. The product has a halogen, which makes this, according to table R, class of compound is the first column, class of compound. It contains a chlorine, which would make this a halocarbon. That was just reading the table and knowing which one is the product. Products come out. All right. Can you put halide also? No, halide is the ions. That would be F minus, Cl minus, Br minus, I minus. These are halides. It is a halocarbon because it's a halogen plus the carbon molecule. Okay. 61 to 65 is another question set. This kind of reminds me of the one from June, right? Many scientists made observations of the elements, blah, 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 modern periodic table. We have groups of 3 elements with similar properties. Groups of 3 elements that have similar properties, and each of these groups is called a triad. Notice relationship between atomic masses and the elements of each triad. Triad 1 consists of sulfur, selenium, and tellurium. The middle element, selenium. Isn't this exactly the question from June? Did we not do this in June? The middle element, selenium, has an atomic mass that is close to the sum of the atomic masses of sulfur and tellurium divided by 2. Example listed. The 80 is close to the 79 when you do the math. The other triads below demonstrate the same mathematical relationship. Identify the triad that contains a metalloid. Okay. Metalloids. You are not a highlighter, but that's fine. Okay. This dark staircase line here, that is where your metalloids are. The metalloids are polonium, tellurium, antimony, arsenic, germanium is a flower, and silicon and boron. Aluminum is a metal. It just falls in a weird spot on the table. So the question is, which triad contains a metalloid? Based on that, we are looking at the first triad because tellurium is your metalloid. So that is triad 1. 61 is triad 1. 62 says explain in terms of electrons why the elements in triad 2 have similar chemical properties. Okay, that is calcium, strontium, and barium. If I look them up on the real periodic table, I am getting calcium, strontium, and barium. They are all together right here in the same group, which is not the answer because that doesn't talk about electrons, but they each have 2 valence electrons. Electrons is the key word. So valence electrons are the outside ones, very last number. 62, they have the same number of valence electrons. If you say just electrons, your answer is wrong because calcium has 20, strontium has 38, and barium has 56. It's that 2 that's the significant part. They all have 2 valence electrons. So they're all looking to get rid of their 2 valence electrons, which means they have the same goal. They are going to bond in the same ways. They're going to try their best to get rid of those 2 electrons. That's why they have similar chemical properties. Number 63, state the trend in first ionization energy as the elements in triad 3 are considered in order of increasing atomic number. Okay, triad 3, we have chlorine, bromine, and iodine. Chlorine is number 17, bromine is 35, and iodine is 53. So that is them in increasing order of atomic number. Electron configurations, it just tells you where the electrons are. So calcium, we did this one earlier. Calcium is 2882. That's because it has 2 electrons in the inner shell. Then it has 1, 2, 3, 4, 5, 6, 7, 8. That's this one. Then it has another layer. 1, 2, 3, 4, 5, 6, 7, 8. That's this one. And then it has another layer. 1, 2. These are your valence electrons. These are the ones that determine what calcium is going to do. If this atom were to be excited, would mean that you added heat or electricity. You add some form of energy. When you do that, one of these electrons is able to jump up to higher levels. They've added in energy. They drank a Red Bull. They have gained wings. They can fly up to higher levels. In this case, your configuration would be 2, 8, 7, 3, because this electron that was in this 8 jumped up. So you subtract an electron from here and you add it there. So instead that would be 7, 3. That's the excited state. The configuration for sodium, for instance. Sodium is number 11. Its configuration is 281. Notice all those add up to 11. Most inner shell, we have our nucleus right here. Inner shell has 1, 2 electrons. Next shell has 1, 2, 3, 4, 5, 6, 7, 8. Last shell, the valence shell, has 1 valence electron. All of these atoms want to have 8 as their last number. Sodium could either try to gain 7 electrons to turn this into an 8, or it can get rid of this and leave this 8 as its valence shell, which is the easiest thing for it to do. So that's why it is going to lose this electron. When it loses this electron, we could basically white out this entire, we can basically white out this entire shell because the shell disappears when it loses that electron. And then our atom has become smaller, which is why we use MELPs for metals. This is metals. Electrons lose. They lose electrons. They become positive because those electrons are negative. When you kick negative people out of your life becomes more positive, and it literally becomes smaller because it's going to lose that valence shell. I've been using MELPs for years because no one has come up with a better acronym, silly way to explain it. MELPs helps. Sorry, that was really lame, but that's the best I got for you. That's pretty much all you need to know about electron configuration. So I'm going to leave it at that unless there's another question, and then I'm going to go back to 63. Okay, it looks like I'm going to 63. All right, so for question 63, what were we doing? Oh, the ionization energy. You can just look this up on table S. Just look them up in order: chlorine, bromine, and iodine. I know that ionization energy is going to go down as you go down the table. There's a lot of chemistry reasons for that. You don't need to know the details, so I'm not going to bore them with you now because this is kind of a cram session. But if you look them up on table S, we are looking at first ionization energy, and then you look them up element by element. Chlorine is 1251. Bromine is 1140, and iodine is 1170. No, iodine is 1008. So it is going to decrease as we go down the table. And you just need to state the trend. Why they give you 3 lines to say one word, I'm not really sure. The answer is just decreases. 64. Compare the volume of a 100-gram sample of the first element in triad 4 to the volume of a 100-gram sample of the third element in triad 4 when both samples are at room temperature. Okay, this is a confusing question, even for me. Compare the volume of 100 grams of the first element in triad 4 to the volume of the third element in triad 4 when both samples are at room temperature. Okay, so we are comparing volumes, and they have the same mass. The mass is going to be 100 grams each. So we are looking at decreasing. It went from 1251, 1140, 1008. Numbers dropping. You just look it up on table S. Okay, so for these, we are doing we're comparing volume and mass. We have the same mass of each, and we need to know what the difference is in volume. There is an equation that relates volume to mass, and that is going to be density. Density is your relationship between mass and volume. So I'm going to look at the density of lithium, which is the first element in triad 4. The density of lithium is, okay, I'm looking it up on table S. Lithium is 0.534 right here. Just looked it up. Density equals 0.534. And for potassium, which is element K, excuse me, potassium is right here. That's going to be 0.89. Your mass is the same. So how is your volume different? So we can set this up and solve it mathematically if you like, or you can just use some math brain and go from there. So for lithium, we're going to use the equation for both of them. We're going to use the equation D equals M over V. Density, we're going to do lithium over here. Density is 0.534. That's going to be equal to my mass of 100 grams divided by some volume, which I'm being asked to figure out. When I do the math for the, wow, throw calculators for fun. That's a good idea. When I do the math for this, I'm going to wind up with 100 divided by 0.534, and that volume is going to be 187.3, and I don't even know what units I'm in right here. Grams per probably cubic centimeter. Yeah. So these are going to be in centimeters cubed. And then for potassium, I'm getting 0.89 is equal to 100 divided by V. And if I solve this, I'm going to wind up with a volume of 112.4 cubic centimeters. This is definitely a part B question because you have to think outside the box. You have to look stuff up on the table. You have to know that density is the relationship between mass and volume. There's a lot of things you have to go into this question already knowing. So definitely a part B question. When you finally get down to it, the volume of potassium is smaller. That 112 is smaller than the 187. So that's all you write. Compare the volume. You can say K has smaller volume. Why can't I write UNE than lithium? And no one says you have to write out the elements. You can just write the symbols. That's fine. And for 65, it says show a numerical setup that demonstrates the mathematical relationship for triad 2. So the relationship is to add the first element and the second element and divide by 2. I'm sorry, add the first and the last. So for triad 2, I'm going to do it on the side here. We have calcium, which is 40. We have strontium, which is 88, and we have barium, which is 137. This says add the first and the last and divide by 2. And it gives you an example of exactly what you have to do. So for the answer, we are going to do 40 plus 137 divided by 2. And the best part about this is that you do not have to solve because it asks you just for a numerical setup. Numerical setup means you have to put in numbers, but you just have to set it up. You don't have to solve. If you want to solve to check your work to make sure that you set it up correctly, that's fine. When I solve this, I'm getting 88.5, which is very close to the 88 that they give you in the question. So based on this example that they give, I would say that I set this up right. Okay. Ugh. We're up to part C. Part C is where you get application questions, how chemistry applies to different subjects, different things. I would say that part B, honestly, B2, the section we just finished, is the hardest part of the test. Part C is scary because it's reading and trying to decipher and understand, but most of the time the questions are a lot easier than they let you think that they are. They almost like try to scare you with all of the reading that you have to do. Okay, so we're reading part C, question 66. wood is mainly cellulose, a polymer made or produced by plants. One use of wood is as a fuel in campfires, fireplaces, and wood furnaces. The molecules of cellulose are long chains of repeating units. That's what a polymer is. Each unit of the chain can be represented as C6H10O5. The balanced equation below represents a reaction that occurs when this molecule is burned in air. Okay. State evidence from the equation that this reaction is exothermic. Now, this is asking you specifically evidence from the equation, which would mean I personally would accept that heat is leaving the reaction, heat is exiting the reaction. If I had to guess, I would say that the Regents wants you to say that heat is a product because that's representative of the equation. So 66, heat is a product. That's simple. Heat is a product. For 67, it says, explain in terms of substances in the reaction why the equation represents a chemical change. Okay, based on the substances in the reaction. This is super simple. New substances are formed. This goes back to probably your first week of chemistry. The differences between physical and chemical changes. New substances are formed. Although I think I did it in January, maybe. Okay. 68 asks you, show a numerical setup for calculating the percent composition by mass in C6H10O5. All right. Percent composition is given to you on table T. Anytime you do math, you go to the back cover, table T. It's part over whole times 100. It's telling you that the whole is 162.1, so you don't even have to calculate that. I know that I need to multiply this entire thing by 100, and the part that they are asking for is the carbon. Carbon is the part. So I have 6 carbons here. My formula is C6. So I have 6 carbons, and each of them has a mass of 12. I know the mass is 12 off the top of my head, but you should look it up. It's right here. Carbon has a mass of 12. You can round that to a whole number. 6 times 12 is 72, I think. Yes, it is 72. So I'm going to put all of my carbons right there. 72 over 162.1 times 100. Now, again, you don't need to solve. It just says show a numerical setup. So that's all you have to do. I would actually make that a percent because that shows you the units. But because percent is a unit, you technically don't need it there because in chemistry, they don't grade you on units. Okay. Next question set, we are looking at 69 to 72. Okay, millions of tons of ammonia are produced each year for use as fertilizer to increase food production. Most of the hydrogen needed to produce ammonia comes from methane gas reacting with steam. This reaction, which occurs in a container under controlled conditions, is shown below in equation 1. It is unbalanced. That's important to know. The reaction that produces ammonia is represented by the balanced equation 2, shown below. A catalyst can be used to increase the rate of the reaction. Potential energy diagram for equation 2 is shown below. Okay, question 69 says, balance equation 1 in your answer booklet using the smallest whole number coefficients. Okie dokie. Here we're getting carbon monoxide, so it's not quite a combustion. Almost, though. Okay, so how do we do this? We have 1 carbon on each side, which is good. If you wanted to, on your test booklet, you can I'm going to do it. CH4 and H2O, CO and H2, and this is how I've always done it. You take this, you split on the arrow. I have CHO. On this side, I have 1 C. I have 4, 5, 6 H's and 1 O. And here I have 1 C, 2 H's, and 1 O. So the question is, how do I fix this? I am going to put a 3 right here. 3 times 2 is going to change that to a 6. And that's it. That's all I had to do. That's the whole thing. So when you balance this, you could put 1s here if you like. If you left them blank, you would still be correct. So that is no problem there. That was it. That's surprisingly easy. Question 70. Explain in terms of collision theory why an increase in temperature increases the rate of the reaction between methane and steam. Okay, collision theory. Basically, the faster stuff moves, the more often it's going to collide. The more stuff there is, the more often it's going to collide. The smaller the volume, the more often it's going to collide. The higher the pressure, the more often it's going to collide. You squish stuff together or make them move faster, they're going to collide more. So, question 70. Why does an increase in temperature increase the rate of the reaction? Particles are moving faster. Particles have more energy. That's about it. There's like 65 ways that you could explain this. So I'm going to write particles collide, because that kind of references that in terms of collision theory. Particles collide more often because they move faster. Boom. That's it. Okay. The next question is 71. Oh boy, we only have 15 questions left. This is awesome. Okay, 71. I don't know about you guys, but my brain hurts. I'm tired of this. State what is represented by interval A in the potential energy diagram. This is interval A. Interval A is just a definition. Do you know how to label potential energy diagrams? It has nothing to do with all of this reading stuff. Like all of this crap that they made you read has literally nothing to do with question 71. This could be a part A question. They just put it in the back because they want to freak you out. They give you an easy question and all this stuff, and it's put there to scare you. So, interval A is going to be the delta H. It's the distance between the products and the reactants. That's delta H. There's like 45 names for delta H. The reason this is a part C question probably is because they usually put that arrow right there and they call it delta H. So 71 is going to be either delta H, enthalpy, heat of reaction, and those are probably all the terms that you know. I would just go with delta H, but that's just me. Okay, and then 72 is a mole ratio question. It says, determine the number of moles of hydrogen gas required to react completely with 50 moles of nitrogen gas in the production of ammonia. So ammonia is NH3, which means we are looking at equation 2. In equation 2, we are producing ammonia. The question is, how many moles of hydrogen would I need if I was using 50 moles of nitrogen? So let's plug in a 50 here. How many moles of hydrogen would I need? It's a ratio. In my regular equation, I need 1 nitrogen for every 3 hydrogens. The question is, how many hydrogens would I use if I had 50 moles of nitrogen? Set those equal. The moles of hydrogen would come out to be 150 just by cross multiplication. 50 times 3 is 150. 1x is just x. X is 150. This is like that question of this chocolate chip cookie recipe I have makes 24 cookies, but how many times do I have to manipulate the recipe if I want to make 48 cookies? If you want to make 48 cookies, you double everything. Here, you want to use 50 eggs instead of 1. So how much hydrogen are you going to get out? You don't use hydrogen for cookies, but same idea. Okay. That is 72. Oh boy. What do we have? 3 sets left, right? Yes, 3 sets left. Okay, there's a lot of organic on this particular test. Like a good amount of organic, which is sometimes good and sometimes bad. Good when they're easy questions that use the reference tables. Okay. 73 to 77. Diethyl ether is used in a lab as an industrial solvent. The boiling point of diethyl ether at standard pressure is 34.6 Celsius. The equation represents a reaction that produces diethyl ether. Identify the element in diethyl ether that allows it to be classified as an organic compound. There was one redox question in part A, and the next question set is more redox. The element that makes this organic is carbon. That's, if it's got carbon, 99% of the time, it's going to be organic. So there you have it. 73 is carbon. Okay. 74. State the number of electrons shared between the carbon atoms in one molecule of the organic reactant. Okay, so you got 3 reactants here. This one is water. That's not organic. Then these are the same. How many electrons are shared between the carbons? Basically, the question is, how many electrons are in the double bond? Each bond has 2 electrons. And if there's 2 bonds, then 2 times 2 gives us 4 electrons. 74 is 4. Question 75. State why the reaction is classified as a synthesis. Synthesis just means formation. So basically all these pieces are being glued together. Not really glued, but they're all sticking together. So how do we explain this? State why the reaction is classified as a synthesis. All reactants form a single product, or something along those lines. 76. Here we go, our first IMF question. Explain in terms of the strength of intermolecular forces why the boiling point of diethyl ether at STP is lower than the boiling point of water. Okay, in terms of intermolecular forces means you have to talk about intermolecular forces. You don't have to differentiate between. We know water uses hydrogen bonding. This diethyl ether, it's symmetrical. If it's symmetrical, that means it's nonpolar. If it's nonpolar, that means it's using van der Waals forces or London dispersion forces. They are the same thing, essentially. So talking about polarity answers a question, but not the question that's being asked. It specifically asks you in terms of intermolecular forces. So just saying intermolecular forces doesn't quite answer the question. It's really the strength of intermolecular force. Oh, I'm dumb. Okay, it says the strength of intermolecular forces. So you could go on a big long tangent and say, water uses hydrogen bonding, which is a stronger force than the force used by diethyl ether, which is van der Waals forces. That's too much writing. And if you got the forces mixed up, then your answer is wrong. For 76, this is the simplest way to answer the question. The intermolecular force, and write it out, don't do IMF, because IMF doesn't necessarily mean intermolecular force. It's something that chemistry teachers use. It's not something that like real life chemists use. So make sure you write it up. The intermolecular force used by water, H2O, is stronger than the force used by, and you could write out the formula, you can write out the words, doesn't matter, diethyl ether. How do I know it's stronger? Because the boiling point is higher. Think of magnets. Magnets and molecules have a lot in common. The stronger magnets hold on to each other. Ow. Okay, strong IMF, not good enough. It needs to be comparative. So it needs to be stronger or weaker. And the context of the question means that you would have to say weaker. If you just put stronger or weaker, then weaker would be the answer, because it's asking you why diethyl ether is lower than water. So your answer would actually be weaker if you just wrote one word. So anyways, think of an intermolecular force as these magnets. These magnets are crazy strong. Okay, I'm going to put that on a ruler. Okay, this guy's at 0. This is 5. 4.5. And they start rolling towards each other. 4. 4 inches apart, and they want to attract to each other. This has a strong magnetic force. It is difficult. I'm wiggling. These are super strong. It's hard to pull them apart from each other. When you have super weak magnets, like those crappy magnets that you get like from the plumber who's like, call me when your sink overflows. Those like super flexy magnets, those are cheap magnets. Those are going to have weak magnetic forces. When they have weak forces, they're really easy to pull apart. Think of a molecule. When molecules are really easy to pull apart, it means that their boiling point is going to be low. It's really easy to get the solid to be pulled apart into a liquid, or the liquid to be pulled apart into a gas. Strong IMFs are going to want to have, they're going to want to stick together. And when they stick together, they're more likely going to be solid or liquid. That's how I know that diethyl ether, because it has a lower boiling point, must mean it has weaker forces. It's easy to pull apart. It's easy to take the liquid and make it into a gas. Okay. Next is 77. We're going to draw a structural formula for an isomer of the product that has the same functional group. Okay, so same functional group means I still want this to be an ether. And for it to have an isomer or be an isomer means it has to have the same formula. So the formula I have is C4OH, well, HO is usually how they do it. C4H10. Oh. So what I would actually do is just pluck off this group and move it over there. It'll still be an ether because you'll still have this oxygen in the middle, and then it has the same formula. I didn't move or remove anything. I just rearranged. So this one I'm going to do and then this is going to be named, not that they asked, but just for your reference. This is going to be this group here, a 1-carbon dangle, is a methyl, and this is a 3-carbon dangle, which is a propyl. I got those prefixes from table P. And then I'm going to put these in alphabetical order. So this would be named methyl propyl ether. They didn't ask, but just so you know. And if I counted them all up, I still have 1, 2, 3, 4 carbons. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and the 1 oxygen. And that oxygen in the middle still makes it an ether. If you weren't sure, why would I change it? They told me I had to. I'm drawing an isomer. So it's the same formula, but it's built differently. I had to rearrange it. Functional group is right here. It's having the same functional group. And ether specifically says it has this oxygen in the middle like this. And R stands for rest of the carbon chain. So on this side, I had a methyl. On this side, I had a propyl. They give it a prime because it doesn't necessarily have to be the same. It could be 2 different carbon chains, but like diethyl ether, it's R and R. In methyl propyl, one's a methyl, one's a propyl. Okay. That is 77. Moving on to the next section, which is a redox, 78 to 81. Okay, it says the electrolysis of brine is concentrated aqueous sodium chloride solution, produces 3 important industrial chemicals: chlorine gas, hydrogen gas, and sodium hydroxide. The diagram and equation below show a brine electrolysis cell. Before the battery is connected, the pH of the brine solution is 7.0. It gives you the diagram, it gives you the equation, and then question 78 asks, explain in terms of energy why this cell is electrolytic. Okay. There's 2 types of redox cells. There is the electrolytic cell, and there is the galvanic or voltaic cell. They're the same thing, just 2 different names. This one is an electrolytic cell because electrolytic cells have a battery because they are non-spontaneous, which means you have to force them to happen. A galvanic or a voltaic cell is just going to happen by its own chemistry magic, basically. Nature just lets it happen. This battery is a galvanic or a voltaic cell. This whole picture is electrolytic because it requires a battery. So in terms of energy, for question 78, the reaction will not happen on its own and requires a power source. You can write non-spontaneous if you like. Reaction is non-spontaneous. I don't think I spelled that right. Or the reaction will not happen on its own and requires a power source. Okay. 79. Explain in terms of ions why the aqueous solution in the cell conducts an electric current. So yeah, reaction requires an electric power source. That's what the battery is. You could also just say it requires a battery. That works as well. Explain in terms of ions why the solution conducts an electric current. Your brain should be thinking electrolyte. Electrolyte doesn't specifically say the word ion. The answer they are actually looking for is that this has mobile ions. Or the solution, rather. Solution has mobile ions. And the mobile ions is what allows it to conduct an electric current. For question 80, state the oxidation number of oxygen in the aqueous product. Okay, so we are looking at the reaction. These are our products. Only this one is aqueous. It is asking what is the oxidation state of oxygen? This is a softball question because if you look it up on the periodic table, according to the periodic table, oxygen will only ever take a charge of -2. It will never take any other charge. So that means that question 80 is -2. You have to have the sign, otherwise your answer is wrong. Now, if you had an element that wasn't oxygen, I'm going to show you how to get it. I'm still going to use oxygen for the example. We're going to use the same thing, but you have a compound. If it doesn't have a charge written on it, the sum should be 0. If I look it up on the periodic table, sodium is always going to be +1. Again, oxygen's always -2. And then hydrogen can be positive or -1. Kind of depends on what it's bonded to. So I'm going to take +1 plus -2 plus some unknown value for hydrogen is going to give me 0. In this case, the hydrogen has to be +1 so that everything sums to 0. That just looks like H. I promise it's +1. 79, the solution has mobile ions. When the ions are swimming around in this solution, like the positive sodium, the negative chlorine, the positive H, and the -OH, that's going to allow your electricity to flow through the solution. That's the definition of an electrolyte. Okay. 81. Compare the pH value of the solution before the battery is connected. It told us in the story that that was 7. And compare that to the solution after the cell operates for 20 minutes. As the cell is operating for 20 minutes, we are forming sodium hydroxide. This OH should tell you that this is a base, and bases have high pH. 8, 9, 10, 11, 12, 13, 14. Those are your basic pHs. So after the cell is operating, the pH is going to be higher. pH will increase. Something to that effect. Okay. And then we have our very last question set. Thank goodness. That honestly was not bad for redox. It's really only have one redox question here. 78 was a redox question. 79 was the definition of an electrolyte. 80 is reading the periodic table. And, excuse me, 81 was an acid-base question. That's why part C is, I think, less scary than B2 because you get a little bit of everything. And they kind of scare you with those stories. If you can get through being scared by the story, the questions are a lot easier. Go over question 80 again. If you look on the periodic table, it's asking for the oxidation state of oxygen. I've kind of circled it, so it's a little muddy here. But oxygen will only ever take a charge of -2. That's what that blue circle is. So that's it. Like nitrogen next to it has 1,000,000 oxidation states, which I kind of went over with this sodium hydroxide example. Because there's no charge on the sodium hydroxide, you assume it's all 0. So then you add up all the pieces and you can figure out that hydrogen had to have been +1 for the whole thing to add to 0. Oxygen was a super, super, super easy element to ask about. They could ask about more difficult stuff, which is why I went over this process. Okay. Dive deeper. Okay, let's say I was looking at H2SO4. Okay, H2SO4. If I look at the periodic table, hydrogen has a few options, sulfur has a few options, and oxygen is always going to be -2. So this is a compound, so the sum is going to be 0. Overall, its charge is 0. So H2 plus S plus O4 has to be equal to 0. I have 4 oxygens. According to the periodic table, each of them is -2. So 4 times -2 is going to give me -8. I'm going to figure out what the sulfur is. And hydrogen is pretty much only going to be positive. I'm sorry, it's only going to be negative when it's a metal hydride. So if I had like sodium hydride, where this one had to be positive and that one had to be negative. Pretty much every other time, hydrogen is going to be positive. So we're going to say this is +1 times 2, because there's 2 of them. It's going to give me +2. I need +2 and -8 and sulfur to come together and cancel out into a 0. So in order for that to happen, mathematically, sulfur, the charge on sulfur in H2SO4 has to be +6. Yes, hydrogen is going to be negative when it's paired up with a metal. And pretty much that happens like 1% of the time. And 99% of the time, it's going to be that +1. So sulfur in this case had to be the +6 to get this whole thing to cancel out to 0. It's a mix of algebra and periodic table. Okay. Glad you remember it. All right, I'm going to move on to this last question set. All righty. We have the isotope radon-222 is produced by the decay of uranium in the Earth's crust. Some of this isotope leaks into basements of homes in the areas where the ground is more porous. An atom of radon-222 decays to an atom of lead-206 through a series of steps as shown on the graph below. Okay, so it's starting out as atomic number radon-226, and then it decays into number 84, decays to 82. It maintains its mass, but it's gaining atomic number, and it's kind of bouncing back and forth here. Okay, so we are asked to determine the number of neutrons in an atom of lead-214. That's question 82. So 214 here is the mass number. And mass number is equal to protons plus neutrons. Now, the mass number that we were given in the question was 214. And I know that the element is lead, Pb. If I look up Pb on the periodic table, the atomic number is 82. That's the number of protons it has. So I'm going to plug that in for P, and I have to figure out how many neutrons it is. So 7th grade algebra, I'm going to subtract the 82 from both sides. Again, I can't do mental math because I was maybe dropped on my head. No one really knows what happened to me. This is 132 neutrons. That's the answer. You just have to know that that 214 is the mass number and what a mass number consists of. So for number 82, we are looking at 132. For question 83, where did my test go? Here we go. Question 83 says, complete the nuclear equation in your answer booklet for the decay of polonium-218 by writing the notation of the missing product. This is where you do some algebra, top and bottom. So we are given this equation. I'm going to rewrite it a few times. So we have 218 and 84 for polonium. That is decaying into lead 214. Holy moly, did anybody just hear my stomach growl? That was embarrassing. You take this equation and you're going to split it into a top and a bottom like this. And then you're going to do simple algebra. You get, and I have to sneeze, oh boy, 218, the arrow is equals 214, oh boy. Ooh, excuse me. You get 214 plus an unknown. We're going to call it x. When you do this math, you are getting x equals 4. So I'm going to put a 4 on top. Then for the bottom, you have 84 equals 82 plus an unknown. Name it x. Do the math. X turns out to be 2. If the 2 is on the bottom, then that means this is atomic number 2. Atomic number 2 is helium. If you don't remember, look it up. No shame in looking it up. Atomic number 2 is helium, so you would put He. And it's that simple. And then you just write that on the chart, on the paper. 4, 2, helium. And that's your finished equation. And we have just 2 questions left, people. All right. 84 says, oh boy, I hate this. Determine the fraction of an original sample of radon-222 that remains unchanged after 7.646 days. Okay, so to do this, we are going to say, I always just set these up in a chart, and every single time it's a little bit different. So we're working with radon-222. And this is going to be the fraction and the number of days. Sorry. So I have 100% or 1/1 of my fraction on day 0. And then the fraction is going to cut in half over each half life. So I'm going to have half of my radon-222, and I'm looking it up on table N. Radon-222 decays at a rate of 3.823 days. So after 3.8 days, half of my radon is still there, and half of it decayed and turned into something else. Does that make sense? It transmutates. It's going to turn into that. It's going to go through this whole back and forth process and turn into different things. But after 3.8 days, half of this has turned into this. Good? Okay. So this is, what is it exactly? 3.82, where'd it go? 823 days. And then in another 3.823 days, I'm going to add it up. 3.823 times 2. This will be the 7.646 days. This fraction gets cut in half again. So instead of being 1/2, it is now going to be 1/4. And the question only asked me to go out this far, which means that my answer is 1/4. And no, you cannot write it in a decimal because it asks you to write it as a fraction. So this is going to be 1/4. And finally, the very last question, it says, explain in terms of elements why the decay of bismuth 210 is considered a transmutation. It's just asking you what a transmutation is. And a transmutation is when one element decays and becomes another element. So, bismuth, or Bi, becomes a new element. You can say becomes a new element. If you wanted to, you could stop there, or you could say by radioactive decay. That's what this equation is here that you did. The polonium is becoming lead, and the decay, the part that's unstable and comes out, is that helium, or those alpha particles. So that is it. The test is finished. It took 2 hours and 52 minutes, which is not bad at all. There's like 3 other reviews maybe that I've done. It records them all. You're more than welcome to go back and look at them. My students in particular, you can text me on Remind if you have any questions. That's about it. I mean, we went over every topic. I would say if you're like last minute cramming, look up vocabulary words, because you can't answer the questions unless you know what the questions are asking you. My students should still absolutely have their vocabulary words somewhere and all their definitions. I don't know where you can find them otherwise, because most of the textbooks have been turned in. You are welcome, Jack and Gerald. Quizlet. Okay, Quizlet could probably have some vocab. I might actually put pictures in Google Classroom of the glossary of a book that I have. They have the Regents vocab. Okay, awesome. That's good to know. I didn't know that. I haven't used Quizlet since college. Okay, so that's it. Study vocab. I would actually, there is a good document. It was put out by Garden City High School, which is not too far from where I live. They have like a 16-page document that will explain the reference tables. Oh boy, sorry. The reference tables is an excellent thing to have under your belt. So you can Google Garden City chemistry reference table, and that'll be like the first thing that comes up. And I know there's also a YouTube video. It's about an hour long, and it explains how and when to use each of the reference tables, because the reference tables and vocabulary is really like 50 to 75% of the test. So if you can really have a handle on those 2 giant pieces of information, the rest of it, it's a very small amount of actual chemistry. and it's a small amount of algebra, which you should already have a decent handle on. So that's what I would suggest. Go find that YouTube video. It's going to be like New York State chemistry reference table. And then same with that Garden City document. It's going to explain how and when to use each of the reference tables. So that's it. And get some good sleep tonight because it's a morning test. Make sure your belly's full. Eat some breakfast. Bring a snack. Eat it in the hallway. I will not be there tomorrow. So pack your own candy to keep you awake and keep you going. And that's it. Best of luck, kids. You are very welcome. See you on the other side.